This brief presentation will introduce you to the concept of virtual work. The method of virtual work is used to solve static equilibrium problems in which the sum of forces in x, y, and z, and the sum of moments about any given point, is equal to 0. The method becomes particularly useful when dealing with static equilibrium of a system of interconnected rigid bodies, as we will see in the following example. Consider the following system with two rigid bars linked at one end, with an external force being applied at the joint, and one bar attached to the wall, while the other interacts with the wall through a roller contact, and finally a spring connecting the two. The problem consists of finding the tension force in the spring that corresponds to the equilibrium position of the system, as well as the equilibrium angle. When doing conventional static analysis on this multi-rigid body system, one should consider all internal forces when doing the sum of forces and movements. If there are large amounts of interconnected bodies, this will result in a lot of work. So, for this type of problem, instead of doing conventional static analysis, we will follow a different approach, the method of virtual work. The method of virtual work states that if a system of interconnected bodies is already in equilibrium under various external forces, then we can assume a virtual or non-existent displacement from the equilibrium position by one of these external forces. When a force produces displacement, work is said to occur. In this method, we are only concerned with forces that create displacement for the system. In other words, we are only concerned with forces that do work. Therefore, all internal and reaction forces and moments are eliminated from our analysis. So, summarizing, only forces that do work on the system are considered. Finally, this work caused by non-existent virtual displacement is called virtual work. The important concept here is that the principle of virtual work states that for a system in static equilibrium, the virtual work created by the virtual displacements will be 0. In the end, the results obtained from using the virtual work principle will be the same as those from the conventional static equilibrium principle. Having said that, let's analyze the same example, only this time using the method of virtual work. Looking at the free body diagram of the system, we have many forces acting on it, some external, some internal, and some reaction. Since reaction and internal forces create no work, because displacement is not possible, the principle of virtual work says that we can ignore them, so that's what we'll do. What we're left with are just the external force and the spring force. Focusing on the spring, the force on top cannot create any work either, because that support cannot be displaced, so we can eliminate this force as well. So we are left with only two forces which are applied on points that could potentially move, therefore potentially doing work on the system: the external force and the spring force on the roller support. Let us assume a non-existent or virtual displacement of the point where the external force is applied. This displacement will be called delta B. This delta B will result in another virtual displacement at the roller. Let us call this roller displacement delta C. We will take the fixed support, or point A, as the origin of our coordinate system. B is the location where the external force is applied, and C is the location of the roller support. We can define D as the length of each link in the system. H will be the unstretched length of the spring, and S the equilibrium spring displacement. Finally, theta is the angle between the horizontal and the first length. So we have that the location of B is equal to the length of D times the sine of theta. Then, a very small virtual displacement, delta B, will be equal to the first derivative of B with respect to theta. Namely, delta B equals D times cosine of theta times delta theta. Doing a similar analysis at point C yields C equal to 2 times D times sine of theta, and delta C equal to 2 times D times cosine of theta times delta theta. Moreover, since H is the unstretched length of the spring, then point C is located at a distance h plus s from the origin. Solving for S yields C minus H, and substituting for C leaves S equal to 2 times D times the sine of theta minus H. Finally, since the magnitude of the spring force is equal to the stiffness constant K times the stretch displacement S, we can substitute and arrive at F equal to K times 2D sine of theta minus H. Now, the principle of virtual work states that if the system is in equilibrium, the total virtual work produced by the external force P and the spring force F over their corresponding virtual displacements should be zero. Since work equals force times displacement, we have virtual work equal to force times virtual displacement. So delta U equals 0 equals P delta B minus F delta C. The work from the spring force is negative because the spring force has the opposite sign from the external force. Substituting, we get PD cosine of theta delta theta minus K 2D sine of theta minus H times 2D cosine of theta delta theta equal to 0. To simplify this equation, we can divide both sides by D cosine of theta delta theta, leaving P minus K 2D sine of theta minus H times 2 equal to 0. From this, we can easily solve for the equilibrium angle, yielding sine of theta equal to P plus 2kh divided by 4kd. This is the answer to the first question in our sample problem. Finally, to find the internal force of the spring, we can substitute this result into the spring force equation F equals Ks, which equals K times 2D sine of theta minus H, leaving F equal to K times 2D times P plus 2kh divided by 4kd minus H. Multiplying and canceling all terms gives the remarkably simple result that the internal force in the spring equals half the external force. This concludes our method of virtual work presentation and example.